Imagine putting a balloon in hot water, it expands. Now put it in cold water, it shrinks. But what if I told you there's a special process where temperature never changes, no matter what you do? Sounds impossible. Welcome to the isothermal process, one of the most important ideas in thermodynamics. Today, you will clearly understand what the isothermal process is, where it happens in real life, how energy flows, why engineers love it, and common mistakes students make. Let's begin. The word isothermal comes from two Greek words. Iso means same. Thermal means temperature. So an isothermal process is a process where temperature remains constant. Even if volume changes, pressure changes, heat is added or removed, the temperature remains exactly the same throughout the process. Mathematically, T equals constant. This happens when the system can exchange heat with surroundings continuously. Let's understand this using daily life. Example 1. Slow balloon inflation. If you slowly inflate a balloon in a room, air inside stays at room temperature. Because heat escapes to the surroundings, the air doesn't get hotter. This is approximately an isothermal expansion. Example 2. Refrigerator cooling gas. Inside your refrigerator, gas expands in a controlled way. Its temperature remains nearly constant during part of the cycle. Example 3. Hot tea cooling in room. If a cup of tea cools slowly, it does so by transferring heat while the temperature moves toward room temperature. Isothermal conditions depend on controlled surroundings. For an isothermal process, we apply the ideal gas law. PV equals nRT. Since T is constant, we get P times V equals constant. That means when volume increases, pressure decreases. When volume decreases, pressure increases. This relationship forms a beautiful curve called isothermal curve on the PV diagram. Unlike straight lines, this curve bends. On the graph, x-axis equals volume, y-axis equals pressure. As volume increases, the curve slopes downward. This tells us the gas keeps doing work, but heat coming in replaces lost internal energy. Result: temperature does not change. Now comes the most important rule. In an isothermal process, heat supplied equals work done. Let's write it simply. Q equals W. This means if gas does work and expands, the same amount of heat flows into the system. So internal energy stays unchanged. Because internal energy depends only on temperature, and here, temperature is constant. Isothermal versus adiabatic. Feature: temperature. Isothermal, constant. Adiabatic, changes. Heat transfer. Isothermal, yes. Adiabatic, no. Speed. Isothermal, slow. Adiabatic, fast. Example: isothermal, piston in air. Adiabatic, diesel engine. Heat difference. Isothermal equals heat exchange. Adiabatic equals no heat exchange. Isothermal processes are used in power plants, heat engines, refrigerators, chemical reactors, aerospace design, cryogenic systems. Especially in Carnot engine cycles, gas storage, material testing. It helps engineers achieve maximum efficiency. Many students think temperature constant equals no heat flow. Wrong. Heat does flow, just enough to maintain temperature. Work is zero. Wrong. Work is definitely happening. Isothermal is not idle, it's balanced. Let's wrap this up. Temperature constant, pressure times volume equals constant. Heat supplied equals work done, happens slowly, needs heat exchange, used in heat engines, gives curved PV graph. Simple, powerful, everywhere. If you love this explanation, hit like, comment isothermal, share with your classmates, subscribe for simple engineering concepts. Next topic. What happens when heat is not allowed at all? Adiabatic process. See you in the next video.